Test, test. Can people on Zoom hear me? All right. All right. Good afternoon. How's everyone doing? Good? How'd Project 3B go? Done? Happy to hear it. As a reminder, we are having a showcase day the Sunday after RR week. So we definitely want to see all the cool things you built. I've heard some really interesting things are going to be showing up there. So you can still work on it if you want. We kind of do this after RR week, so you get a bit extra time. You don't have to just show us what you submitted to Gradescope. If you want to keep building on it, then that'll be great. Yeah, this is a good way to like build your first personal project. Just starting off from there. All right, so today's lectures are all going to be optional. That doesn't mean they're not important. They just kind of cover things that we don't consider within the core of the class. They'll be useful, interesting kind of deep dives into some other like obscure topics in computer science. Mainly, you just don't need to take notes for this. It's not going to be tested on. So just sit back and relax. Enjoy this stuff we talk about this week. So today's main topic is going to be on compression. So how many people have used a zip file before? Yeah, a lot of people. In effect, what a zip file is a way to compress an existing file into a smaller format. So there's this zip command that if I run on the entire text of Moby Dick, it transforms the text file that's originally 643 kilobytes down to 261 kilobytes in size. So about 60% of the data that used to be in mobydick.txt was removed, but it's still there. It's just compressed. The information present is the same because if we unzip, then we're able to get back to our original data. So the idea is somehow we're able to transform something that took 600,000 bytes worth of data and smushed it down to 260 bytes without changing anything about it. That's kind of our goal for today. So here's kind of the general approach or kind of the theoretical model we're using. We take a long string of bits, we apply this compression algorithm, and then we get a compressed sequence of bits. So ideally, C of B is shorter in length than the original B. And we need this to be an injective function. We need to be able to go backwards. We need to have this counter inverse algorithm, which takes our compressed bits and unfurls it back into our original large size. Now, in general, text files tend to be very highly compressible. If you're dealing with actual real-world data, like the text of a book, you're going to get compression rates around 70% or more. It is effectively possible to compress things. So let's take a look at how we can actually do this. So before we talk about how we compress stuff, we should talk first about information theory. So intuitively, when we compress some data, we're not changing the information that's stored there. We're just writing it in a shorter format. In effect, the information that we have should stay the same. And we need to first figure out what we mean by information. One useful metric that I use for information is to just see how easy it is to memorize things. Now, this isn't precise. Human brains are very different in how they memorize things than the computers. But it's a good approximation to see how much information is stored there. If it's easy to memorize, then it generally has less information. If it's harder to memorize, it generally has more information stored in it. So let's do some examples. Here is a 10-character string. I want you to memorize this. All right. Let's take 30 seconds. Try to memorize this. And on the next slide, I'll give you a chance to recite it. All right. What was the string? BXXONHPWTP. Yeah. How do you feel about that? How easy to memorize, hard to memorize, kind of in the middle? All right. Let's try a longer string. Let's try a 34-character string. 47, sorry. All right. What was the string? One, a poem, a raven. Midnight so dreary, tired and weary. Yeah. How was that one? Kind of in the middle? Which one was harder to memorize? The 10-character string or the 47-character string? How many people say the 10-character string was harder to memorize? How many people say the 47-character string was harder to memorize? Looks about even, actually. Some people found the first one easier, some people found the second one easier. You want to go bigger? Let's go for a 10,000-character string. All right, you ready? I'm only going to give you 5 seconds for this one. All right, go. Ah! Playing music. No, I'm not playing music. Was that easy to memorize? Yeah. So it does seem like the number of characters that you have isn't actually a good metric of how difficult something is to memorize. That's because they have different amounts of information. This thing had a lot of information per character because it was effectively random. I picked random characters. I actually use a Python script to generate a random string of characters. So it's very difficult to memorize characters in this form. This one, it at the very least has some meaningful data associated with it. Out of curiosity, does anyone recognize this excerpt? I took this from somewhere. Huh? It is not Edgar Allan Poe. It is a parody of The Raven, but it's a very specific parody of The Raven. Anyone have a guess? So this is actually from a book titled Codaic Cadenza. It is a sequence of stories that kind of parody various famous like poems, and it's written entirely in Pilish. So Pilish is where each word, if you take the length, you get the digits of pi. So you have 3 for 1. The next is a 1-letter word, then a 4-letter word, then a 1-letter word, then a 5-letter word, then a 9-letter word, then 2, 6, 5, 3, 5. This goes on for 8,000 words. Yeah, and throughout it all, it's parodying various poems. It starts off with the Raven. I think it goes into Jabberwocky eventually, and then it keeps going. Interesting thing that you can actually store some extra information in a poem. So in effect, like the original Edgar Allan Poe piece, it was designed to talk about the Raven, but you can rewrite the Raven in a way that it stores additional information. So that indicates that we're not storing maximal information in our data set. Meanwhile, this one, there's way less information than there are characters here. So in order to define what information is formally, we're going to have to define entropy. In CS, a bit is a single binary digit. Most computers use bits to store information, so ones and zeros. And by default, the way that English text gets represented in a computer is by 8-bit sequences. Every single letter is stored as 8 bits of data. The information that gets stored is actually generally less than this because data tends to be predictable. The more predictable a data set is, the fewer bits of data it's actually going to need to contain. Here's kind of the formal definition of Shannon entropy. Don't worry if this goes a bit over your head. This is it's a very formalized definition. In effect, if you look at the probabilities that each possible value could be, right? So what is the probability that the next value is a 1 versus a 0? And you take the expected value of the negative log of this. I believe it's the negative, I think it's the negative binary log here. It might be the negative natural log. I don't remember. But either way, if you take the expected value over that, then you get a sense of about how much information is stored in it. If you have a 50-50 chance of being a 1 and 0, this equation evaluates to 1. So you have 1 bit of entropy for a completely random bit. If you have 100% chance to be a 1 and a 0% chance to be a 0, that is going to equal 0 bits of entropy. So that means there's no information inherent to that because it's perfectly guaranteed it was a 1 there. In a way, it's a measure of how many possible strings exist that fulfill that characteristic. So kind of the unpredictability of the string. So if a string has 10 bits of entropy, that means that there's 2 to the 10 or 1,024 different possible strings it could have been. If you take a 10-character string of random letters, there's 26 to the 10 possible strings. So the entropy is just about 47 bits. On the other side, that 10,000 character string, there's only 26 possible strings that could have existed of that, right? 1 for each possible letter. So there's only really 4.7 bits of entropy in there. That's why the 10,000 character string was easier to remember than the 10 character string. Now, English text is somewhere in the middle. It's not going to be a sequence of A's. It's also not going to be a sequence of random letters. So there's going to be an entropy level somewhere in between. Now, one way we can measure this, and this was an actual experiment done, is you try to remove letters, and you try to see at what point is it impossible for a human to reconstruct the original statement. So here I've done something similar. I've erased a bunch of letters at random from this string, and I want you to tell me what the original string was. Let's take a minute or so to try and figure out what this original string was. I'll come back after. All right, let's bring everyone back. What does it say? When writing English text, most characters can be omitted without losing meaning. Yeah. Here's a full string. So we can see that a lot of these characters don't actually need to be included, and you can still reconstruct the data. In fact, there's some of these words that I entirely deleted, and you were able to figure out what it was. So that goes to show you that, in theory, there's less information present than actually exists in standard English. And what's interesting is, if I can delete these characters and you can still reconstruct it, that is a way of compressing the data itself, right? Like, I can delete these characters from my compressed file, and I can figure out a way to uncompress it by adding those letters back. So that's one example of how information theory can lead to compression. Now, if you play through these thought experiments, you do an actual controlled psychological survey on this, it was determined that English has about 1 bit of entropy per character. So if you have 47 characters of English text, that's about 47 bits of entropy, about the same as the 10 character string. That's why it felt about equally difficult to solve both of them. About half of you thought that the 10 character string was easier, about half of you thought the 47 character string was easier. So that's kind of in between there. So in theory, an optimal compression algorithm should be able to compress a 47 character string of English text to about 47 bits of data. Practically, that's not really going to be feasible. You are going to get stuck before that limit. But you can get fairly close. If you just look at the relative frequencies of English characters, you can get a Shannon entropy of 4.1 bits, so you can go down from 8 bits to 4.1. If you look at relative word frequencies, you can get down to even 2.6 bits per character. Now, as we compress data, the entropy is going to stay constant because we still want to have the same set of values possible. So that means that the more we compress our data, the more uniformly distributed our bits are going to end up becoming. It's going to be more probable that you have 50-50 shot out of 1 or 0 next, because we kind of get rid of those high probability 1s or high probability 0s in our data. So let's take a look at how we can actually accomplish a compression algorithm. So by default, we have 8 bits per character. We are going to try to reduce this down to as few bits as possible. Now, an easy way to compress is to just use fewer bits. 8 bits has 2 to the 8 different values, 256 possibilities. How many letters are there in the English language? 26. If we're assuming we're only sticking with lowercase symbols, then yeah, only 26. Why are we using 256 possibilities to store 26 different things? So we could use fewer bits. And generally, we'll say which code words go to which symbols. Here's an example of how we can possibly do this. How many people are familiar with Braille? Yeah, it's kind of a way to like write English letters in a tactile sense. But if you look at it from an information theory perspective, it's effectively a way to write down a single letter in 6 dots. And each dot can be raised or unraised. You can imagine that you translate that into 1 or 0, and that takes each letter to 6 bits worth of data. Now, if we go further, we can get down to 5 bits, but we can't get any further. Can anyone explain why that's the case? Yeah. Yeah, 2 to the 5 is 32, 2 to the 4 is 16. 16 is too small to fit 26 different possibilities. So we could get down to 5 bits, but that's not enough. I want to get closer to 1 as possible. One approach instead could be to use a variable number of bits per letter. Like some letters are more common than others. So what if we use, for example, less bits for E and more bits for Z? Can anyone think of a cipher that does this? Yeah?
Morse code.
Yeah, Morse code. Yeah, Morse. Yeah. Here's an example of Morse code where each letter uses between 1 and 4 bits worth of data. It's very useful in that a lot of the short letters, the most common letters, are short. You can see E is the most common letter in the English alphabet, followed by T, and then A, then O, I, N, S, H, R, D, L, U. Most of those letters are either very short, or in the case of O, a very consistent, easy to remember sequence. It's actually surprisingly easy to memorize Morse code once you learn some of these tricks. So E is like the single dot, T is the single dash. There's a lot of these small letters. Unfortunately, there is somewhat of a problem. As an example, what is dash dash dot dash dash dot? What does that mean? This is an English word. What word do you think it is? Mean? Yeah. Any other words could it be? Gigi? Yeah. Anything else? Those are probably the easiest, like, simple words. Man is a good one. Yeah. Yeah, there's a lot of variable words. It's also mate. It's ambiguous what word we're referring to, which is bad for a compression algorithm. If this dash dash dot can be unambiguously assigned one of these 4 things, then this isn't a valid compression algorithm. It's lost C. We've lost information somehow. Now, in practice, the way that gets done is that operators pause between each code word. There's actually a very specific amount of length you're supposed to be using between for each dash, each dot, the space between the spaces in a letter, the spaces between letters, and the spaces between sentences. But if you just look at the dashes and dots as purely binary, then you do get this ambiguity. Out of curiosity, I went through like a crossword dictionary and I tried to find the most ambiguous string I could possibly find. The most ambiguous one is dash dot 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 dash dot 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 dot, which has 23 different representations in the English language. So have fun finding all of those. An alternate strategy, so instead of just using Morse code, we are going to have to deal with this case where sometimes these are ambiguous. So we need to find a way to make our code entirely unambiguous. One of the ways we can do that is through the use of a prefix-free code. So here's another way to describe how Morse code works. In a way, you start at the start, and then you move left for a dot, right for a dash. And one thing you note, one of the reasons why we had this issue was that if you start a letter and keep going down to, say, B, the first part of that word could have possibly been a T or an N or a D. And once you have that possibility, then you now start looking at like possible like splits of letters. Like maybe this is an entire B, maybe it's a T followed by another piece of a letter. And that's what was causing that ambiguity. If instead we set it up so that none of these paths had more than one letter on it, then we'd be able to get a perfectly unambiguous encoding. So that effectively means that we want a tree where letters are only on the leaves. Here's an example of one that you could use for English letters. You start, if it's just a purely one, then you have space. If you have 0, 1, that's an E, 0, 0, 1, that's a T, 0, 0, 0, 1, that's an A, and so on. If I gave you the string I8, that compresses to this particular string here, and this string is unique. No matter how you try to read it, there's only one distinct way to read it. Because if you look at the first part, you have 5 zeros followed by 1. There's only one possible letter in existence that could possibly be that, and that's I. After that, there's nothing further down there. So you now move to the next letter. You get a single 1, that's a space, and then you keep going. This is perfectly unambiguous. Is this a good compression algorithm? No? Why not? Yeah, it's not really bushy. And this feels like something where bushiness is probably going to be a good idea. Yeah. Here's another example where we actually have something bushier. It's similar in the sense that we don't have any letters in any of the internal nodes. They're only on leaves. And if you look at this, you can actually show that this is the unique sequence that provides this. I8 is this sequence, and this sequence is exclusively I8. There's no other string that could possibly be this. So which one do you think is better? What do you think? Number 1? Number 2? How many people think it kind of depends on the data? Yeah, it actually kind of does depend on the data. For example, if I wanted to write eat, that's 15 bits on the left side, but 20 bits for the right side, because this string has so many e's. On the other hand, if I'm working with the word Josh, Josh has so many bits on the left side because J is a very, very uncommon letter. It goes all the way at the very end, and it has 48 total bits. Whereas the right side, Josh, is 23 bits, much smaller. So it might actually be better to actually calculate what the best code is for a given text. It might differ depending on which text we're working with, right? If we're talking about quails and zebras in Zimbabwe, then you're going to have a very, very different letter distribution than if you were talking about any other text, because you'd have way more Q's and way more Z's. So what we can do is we can kind of create an algorithm that, based on the text, determines the best prefix free tree for it. So let's try it out. To start off, I'm going to try to maximize the entropy per bit. I want as close to 50% zeros and 50% ones as possible, because that increases the entropy as much as possible per bit. And since the entropy needs to stay constant, if I increase the entropy per bit, that means that I'm reducing the total number of bits I need. So first off, I'll count all the relative frequencies of the characters in the text, and then I'll try to split it into left and right halves of about equal frequency. The left half will get a leading 0, the right half will get a leading 1, and we'll just keep going until everything is in its own separate leaf. So let's try it out with this example. Here I've split up a string of Chinese characters into these 5 types of symbols. And here are the frequencies that I've come up with. So first off, I'm going to try to split things into roughly even values. And the easiest way I could do this is I could split 35 into 17. That forms 0.51. Is that right? 0.52, sorry. And then the last 3 characters, I'll split into a separate branch. That's 0.48. So this is about a 50-50 split. It's as close as possible as I can get with this data set. So I split it into this. Then I just recurse. What do I do for the left half? How do I split this? Yeah, I split the three and I split the first character and I split the second character into two pieces. That is as best as we can get. We can't get any better because the three is just so much more frequent. What about the right side? What's the best split we can get here? Yeah, we take the first one and we take the second two, we split it. That's the best we can get. It's kind of unfortunate that we have three things that are all just about equal in size. So the best we can do is split it that way. So we split like this. We split like this. And then what do we do for the last one? Split it into two again. Yeah. So if we do this, then here is our Shannon-Fano code. We have 0, 0 for the first character, 0, 1 for the second, 1, 0 for the third, 1, 1, 0 for the fourth one, and 1, 1, 1 for the fifth one. How do people feel about this? Is this a good approach? What do people think? Think this is good? Think this is bad? Not sure. Well, at the very least, it does compress stuff, right? If you remember, Chinese characters take what, 40,000 possibilities? Which means that if you're trying to write it out in practice, you need at least 16 bits of data to store any possible Chinese character. In practice, Unicode uses somewhere between 16 and 32 bits, depending on the character that you're dealing with. So we are getting this down to 2 or 3 bits at a time. That's fairly good. Unfortunately, it's not optimal. CS170 will teach you a better way, or actually, we'll teach you a better way now. Well, CS170 will teach you to prove that this is not optimal. As it turns out, the optimal solution is a slightly different approach. And this is called Huffman encoding. Now, I'm just going to show you this algorithm. It is a bit hard to create this algorithm from scratch, and doing the math to show that it's optimal is beyond the scope of this course. So let's just try describing what this algorithm is. So let's say that I have a text file with these 5 characters. 35% of them are this first character, which means 3. So what we'll do is we'll assign each symbol a node with a weight equal to its relative frequency. And what I'll do is I'll just take the 2 smallest nodes and merge them together into a node with a weight equal to the sum of those weights. And then I'll just keep doing that over and over until we get a full tree. And then I'll assign strings for each of them based on that. So let's start off with the first part. What are the first 2 things that I merge? 16 and 15? Yeah, those are the 2 smallest. So I'll merge them into a mini tree that has total weight 0.31. What do I do next? 17 and 17. Yeah, those merge to form a 0.34 node. Now what? 0.34 and 0.31. Yeah, those are the 2 smallest, so we merge them to form a bigger node of 0.65. And then, yeah, 0.35 and 0.65 merge to form our final tree, like this. And then we just assign zeros and ones, depending on whether we move left or right. Let me ask this. How many bits per symbol do you need to compress a file with this frequency? Let's take a minute or so to try and figure this out. All right. How many people say it's A, that it takes 2.6 bits per symbol? How many people say it's B, that it's 2.3 bits per symbol? How many people say we don't have enough information, we still need to know the exact characters in the exact order? All right. What more information do we need to know? Anyone who said that you need more information? What more information do you need to know? The exact characters in the file? Well, let's think about this. If you look at each character, we know its frequency. And does it matter where the characters are in the file in terms of its size? No. We can have a fully shuffled ordering for the characters, and won't change the total number of bits we use because we use the same number of bits for each character individually. So as it turns out, we do have the information we need here. We just need to count out the frequencies of each one. So if we assume we have, for example, 100 symbols, we can say that we have 35 bits to store the first character, 51 total bits to store the second one, so on and so forth. In total, we have 230 total bits, and 230 divided by 100 is 2.3 bits per symbol. So using this approach, we average 2.3 bits per symbol. That's fairly good. Now, if we had this file that contained 1,000 characters in this frequency, how many total bits would we need if we encoded this using 32-bit Unicode? Anyone want to say? A 1,000 characters, each character takes 32 bits of data. So how many total bits would you need in this case? Yeah. 32,000? Yeah, 32,000 bits. What about using the Huffman code, which we said has 2.3 bits per character on average? Yeah, 2,300 bits. So in effect, using this encoding, we managed to get 14 times more efficient space use. So 32,000 brought down to 2,300. That's a 14 times improvement. Now, the slight issue is that we can only encode strings with these 5 particular characters. And I don't know many Chinese sentences that use only these 3 or these 5 characters. And it's really only efficient for this particular frequency distribution. If you had a different frequency distribution, then you are going to have a different optimal tree. Now, if you use the Shannon-Fano code that we described earlier, then you evaluate to an average of 2.31 bits per symbol. Meanwhile, the Huffman encoding was 2.3 bits per symbol. And if you look at the Shannon entropy, the actual entropy of the data set, then we get 2.233 bits per symbol. So this is actually really close to the optimal solution. In practice, the reason why we can't get down to 2.233 is because we can't store things with a fractional number of bits. If we were able to store things with a fractional number of bits, then we would be able to get closer. But unfortunately, we only have a discrete number of bits per character. So we kind of have to get a bit close, but not exactly there. As it turns out, the Huffman code is optimal given a data set with a given set of frequencies. So it's going to be strictly better than the Shannon-Fano code. So there's basically no downside to using the Huffman code. So how can we actually build this? If we know that we want to set up a prefix-free code, what data structure could we actually use to build this thing? Anyone have any preferences? Hash map's good. We do kind of want kind of map. But I kind of want something slightly better. Any other ideas? Tree map? Why tree map versus a hash map?
Because it kind of follows the same idea of the structure that we were building earlier, where like the left represents one side of the branch and the right represents the other.
That is true. We did see that it looks kind of like a tree, but that's not quite a tree map. What is it actually? It is a trie. Yeah. Yeah, we could do a bunch of different things. We could use all of these, but this actually is a trie in a way. So we could encode things using a hash map. Decoding is going to be much better done using a trie. Yeah. In effect, we're just looking for the longest matching prefix. And that is an operation that tries are really good at doing because you follow down the path, looking one character at a time until you hit the right, until you hit a leaf. So here's an I, here's a space, here's an A, and so on and so forth. Using this, we are able to get a really efficient compression algorithm. So there's a few possible philosophies on how to do this. One approach is you take every possible input type, you take a huge number of samples on every single case of this, and you just create a standard code for every single possible type. So I might take all the English text in existence, generate a single tree for all English text, and use that for every time that I'm dealing with English. Another possibility is I try to create this Huffman code for every single file that I'm trying to compress. I want to know, what do you think are the good approaches? What are the advantages of each possibility? Anyone want to suggest an advantage for either way? There are advantages and disadvantages to both. Yeah, you have one?
So if you use specific code, your compression would be faster overall.
One, compression will be faster. Yeah. There was something in the back there. Yeah.
Yeah, like if you're doing the first one, you wouldn't have to compute the try every time. You already have it like saved.
Yeah. Don't need to recompute anything. Anything else? Yeah.
If you do it specific for each one, then it would take less bits to input the information because it's not using character. It's not words that are not going to be in the file.
Yeah. So if you do the first one, then you don't need to send the code along with it. Are there any advantages for 2 over 1? Yeah, compression is better, which is probably going to be overall end up using less space if we have a long enough file. Yeah. If you don't send the tree or it gets corrupted, the file can't be uncompressed, even partially. Yeah. Which one do you think gets used more often in real life? Number 1 or number 2? How many people say 1? How many people say 2? Yeah. As it turns out, here's what I'm looking at. Option 1 is going to result in a suboptimal encoding, so it's going to be worse in encoding. But option 2 is going to use extra space, and it's also going to take extra time to run. But generally speaking, for very large inputs, the cost of the table is going to be insignificant, so you do prefer option 2, just to reduce the space even more. And we don't actually care too much about how long it takes to compress things, as long as it compresses things in a reasonable time. Actually, modern compression algorithms, I think 7-zip, you can choose how long you want it to take. And depending on the setting you set there, it'll compress it more or less. Yeah. Do you have a question? Yeah, it's also kind of hard to consume every single English text in existence. But I mean, at least once you do it once, you don't need to do it again. So you can imagine that some really clever scientists in the 1980s might have come up with the plan. The same way with ASCII, right? Like ASCII is a way to assign every single letter in English to a particular 8-bit sequence, and we still use that because no one wants to update it. Yeah. Internet is the same way. There's so many things that we would do differently if we could just throw out the internet and start afresh. It would be way more secure, and you can talk about 161 all day about this. Yeah. So in practice, philosophy 2 ends up getting used more frequently in the real world. We don't care as much about the initial startup cost, and we care a lot about the extra compression that we can get for long files. So here's kind of how you're going to end up compressing things. You get an input text. I'll count all the frequencies. I'll build the encoding array and the decoding trie. And then I'll write the decoding trie first, and then I'll write the code words after there. I need some data to show here's the end of the trie, and I need to find some way to write the trie in binary, but that's possible. you can assume that that is a possible solvable problem. When I decode something, or when I'm decompressing something, what I do is I first read the decoding try. I construct it in my computer's memory, and then I use the code word bits, just walking down the try, getting individual letters. Now, if you think about it, printing out data, computers don't actually understand what we mean when we say print out data. They were just told to print out a sequence of bits. And we're told that the way you print out the sequence of bits is you draw the sequence of pixels. And that sequence of pixels just happens to look like a character that makes sense to humans. Computers don't actually know any of that. They just know if you're given a sequence of bits, here's a pixel sequence. So that's just kind of an interesting way to view how a computer thinks. Computers don't actually know what they're doing. They're just doing what they're told. And if by chance it happens to look like something useful for humans, then good for us. So here's the overall process. We take a file, that's a text file, for example. In order to compress it, we take each b-bit symbol. We consider all the possibilities. We use a Huffman encoding scheme to create a decoding try and encoding map. And then we just store all of them this way. To decompress, we just kind of reverse the process. We take the try, extract that into our computer's memory, and then apply longest prefixes over and over until we get the full data set back out. Now, this is just one approach that you can use to compress things. There's a lot of different ways you can do this. You have run length encoding, which is an option. You have LZW, which is another option. All of these are more complicated versions of the same idea. And generally speaking, most modern compression algorithms use a combination of these. Zip files, 7-zip, they use a lot of these in practice. Generally speaking, our goal is to exploit all of this redundancy, the existing order, to get rid of all these low entropy sequences. On the other hand, if you have a data set that is completely random, then there's actually a chance that this increases the size of your data set. If you just type in python.random sequences of letters and then try to compress it in a zip file, then you might actually increase the size of the file slightly. And there's actually a good reason why. Different compression algorithms are going to achieve different compression rates on different files. We'd like to compare these in some way, but it's not really easy to say just purely every file can be compressed by 50% using this compression algorithm. In fact, that's actually impossible. Let's start off with a puzzle. Let's say that I'm talking to someone and they say, hey, I've created a new compression algorithm. It's called SuperZip. And I guarantee that it can compress any file you give it by 50%. Guaranteed. And I'll let you see it for only $1,000. Now, I am a scientific-minded person. And if there's a chance that this is possible, then I'd like to see this algorithm. This looks pretty cool. See? And I can probably compliment Karma for $1,000, right? If it's something entirely new. So what do you think? Can I provably state that it's impossible before I even see this? Yeah?
It would end up being infinite compression since you could just take a file, compress it by 50%, and take that, and then compress it again by 50%. Just keep on going infinitely.
Yeah.
One bit.
Yeah, so I'm going to counter this person. Well, hang on a second. That's not possible. Imagine that I take some data set that's 1,000 bits long, and I send it into your file. That'll get me 500 bits. And then I compress a second time, that gets me 250 bits, and I keep going. Eventually, I'll get down to 1 bit. That doesn't make sense. How do I take a 1,000 bit thing and turn it into 1 bit? All right, so this other person says, okay, fine. Actually, you can only apply this once. This only works one time. If you try to apply it a second time, it's not going to compress any further. But otherwise, this is going to work. It's going to guarantee 50% compression. Is this still impossible?
I mean, the counter, you can use a counter example if your original data is 1 bit. then there's just no way to compress that way.
Okay, yeah, okay. This doesn't work on 1-bit data files, but like, who's gonna compress a 1-bit data file anyway? All right.
Generally, you're going to need some sort of decompression algorithm that takes any like n-bit sequence and gets you like everything back. So whenever you're compressing even once by 50%, you're like losing 50% of the data. So you're going to have as many possible outputs that you can't get back to the original twice as many inputs.
Yeah, that's an important point. We mentioned that in order for this compression algorithm to work, we need to be able to decompress it back, which means that this needs to be injective. If we take 2 different bit strings, we need to get 2 different outputs. And let's take a look. If we have 100, if we take a set that's 1,000 bit strings, then there's 2 to the 1,000 different possibilities. How many possible 500-bit strings are there? 2 to the 500. Even if you add in all the smaller bit strings, there's only 2 to the 501 minus 1 bit strings. So that is 2 to the 499 times smaller than the original data set. So if you have 2 to the 1,000 things and only 2 to the 501 places to put it, then you're not going to be able to put each thing in its own unique place. It's not quite half. It is much worse than this, because this has an exponent in there. Yeah. So basically, out of our 1,000 bit inputs, only about 1 and 2 to the 499, which is effectively none of them, can be compressed by a factor of 50%. This brings us to this theorem. In general, no compression algorithm can compress data below the entropy of a data set. Once you hit that entropy limit, you are done. It is impossible to compress further. In fact, you can go even further. So first of all, if you want to look at every possible string of length n bits, then that will form a data set with n bits of entropy. So there's 2 to the n distant possible ways. So you can't take any compression algorithm that takes every n bit string and reduce it to this. On average, any compression algorithm is going to keep the same number of bits. In fact, we can go even further and say that on average, any compression algorithm is going to increase the size of the average string. There's actually no way to create a compression algorithm that gets exactly the same average as the original uncompressed version, except for the compression algorithm that just takes in your input and outputs it directly back. There's an actual proof that shows that this is the case. If you include the compression algorithm as part of the file size, pretty much any compression algorithm will on average increase the length of random input. But the reason why we can take advantage of this is that only a small fraction of all possible strings are actually valid English sequences. That's why we can end up creating this compression algorithm. We'll take all the low entropy strings shorter, and we'll take all the higher entropy strings and make them longer. And that's perfectly fine because all of our data are short low entropy strings. So generally, the more predictable the data is, the less information it'll actually carry. And fortunately, pretty much anything that's meaningful is going to be low entropy. It's kind of ironic that the more meaning you assign to some data, the less information it actually carries. And the most information you have is a data file that's completely random and has no meaning. But that's what ends up happening. Now, generally speaking, compression can be slow. Slower algorithms yield better results. But regardless of what we do, we can't get down to beyond the Shannon entropy limit. You might be asking if it's possible to write the best possible compression algorithm, even like including arbitrary time. As it turns out, it is not possible, not easy anyway. It actually plays into our next topic, which is going to be P versus NP. All right. That's it for today. Thank you.